Now let's prove this question. Let's say U is a solution of the Poisson equation given here. If it's in the boundary, then the Laplacian is equal to rho. If it's on the boundary, if it's in the interior, then it's rho. If it's on the boundary, then it's F. Okay, that's what this means. And if phi of V is the Dirichlet functional, and we set A as the set of all functions satisfying continuity conditions, and evaluated on the boundary is F, then our U, which satisfies our Poisson equation, is actually the minimizer of big phi of V. Okay, so basically this means, in other words, U is argmin of phi V. Okay, so to prove this, I'm going to use Green's first theorem, or first identity. And Green's first identity actually comes from, actually this is easy to prove. Maybe I'll do another video on the proof, but for now, just think of this as the multivariate equivalent of integration by parts. So remember what integration by parts was? It comes from the product rule, right? So this is f g prime plus f prime g. Okay, now pretend like f is v and g is nabla of u. Then, okay, so maybe they're not equal, maybe they're analogous. So maybe the derivative would be like the second derivative of u, right? Which is kind of like the Laplacian. And the derivative of f, because v is a vector, would be like the gradient of v. And if we add two more integrals to everything, then maybe you can see how integration by parts is similar to Green's first identity. Of course, there are some things we need to keep in mind, such as performing a dot product instead of a regular product, but that's just because we're dealing with vectors here. Okay, so for now, let's just pretend like Green's first identity is integration by parts without proving it. And now let's set out to prove it. Okay, so first of all, we're given that the Laplacian of u is rho. What does that mean? It means that if we subtract rho, this is 0. Now, this means that if we multiply 0 by anything, we'll still get 0. So let's pretend like, let's assume phi is a function chosen from our set A. Okay, so basically what this means is phi evaluated on the boundary is f, okay? And it satisfies continuity conditions specified here. Anyway, if phi is any function, an arbitrary function from A, then we can write 0 times u minus phi is still 0. And so if we take the integral over the region, that's still 0, right? This is all still 0. Okay, now we are going to use Green's first identity. But here's the good thing. We can ignore the left-hand side. We can ignore it. Why? Okay, here's what I'm going to do. I'm going to pretend like, here's what we need to notice. U minus phi evaluated on the boundary. What is u evaluated on the boundary? It's given by the initial condition here. That's f. Phi, being a function in A, by definition evaluated on the boundary is f. So this is just f minus f, or 0. So whatever we get on the left-hand side of Green's first identity, we're evaluating it on the boundary, and therefore we don't need to consider it. It's just going to be 0, okay? So this part is going to go away. And now, what do we have? We have, pretend like this is v, okay? Pretend like this is v. Okay, actually, let me first multiply this out, distribute it. So I'll get negative Laplacian of u times u minus phi. And then I just have rho right here. Okay, so hopefully you're following. I'm going to use Green's first identity on this part of the integral. This part I'm just going to leave as is. Okay, so by Green's first, I'll have, so pretend like this part right here, pretend like this part is v, okay? So we have negative Laplacian of u times v is, by Green's first, is going to be positive because I move this part over, because this red part became 0. Now this is positive gradient of v times, or dot producted with, gradient of u. Okay, and this part I'm going to leave as is. So that's where Green's first identity was used. Okay, now let's actually distribute the dot product. What do we get then? We get u dot u minus nabla phi dot nabla u. And then from here we have minus rho u, and then we'll have, maybe I can write it this way, minus rho phi. Okay? So I just rewrote this part in here and here. Okay. Now all of this is equal to 0, so let me bring these two parenthesized objects onto the right side, onto the left side. Then what will I get? I'll get the triple integral of del phi dot del u, I'm running out of space, okay, minus rho phi is equal to the triple integral of u, and then minus rho u. Okay, all I did was I moved these two bits here onto the right side of onto the left side of the equation. Okay, now I am going to claim that this is less than or equal to the triple integral of, let's see. Okay, so maybe I should write this on the left side, on the right side, to make things more clear. Okay. So I'm going to say that this is less than or equal to, let me make that smaller, this part, the second part, I'm going to leave as is. But this part is going to be less than or equal to half of the size of Okay, I'm running out of space again. Sorry for all this adjustment. The size of phi squared plus 1/2 the size of u squared. Okay? Now, once I show this, okay, I haven't shown this yet, and so I'll write this in white. This inequality I haven't shown yet, but once I show it, I will be done. Okay? I will be done because this implies phi of u. What is phi of u? What is big phi of u? It's going to be, by definition, 1/2 of the size of u squared minus rho u. Okay. So based on this inequality, what I'm doing is I'm moving this 1/2 size of u. I'm going to erase this for now. And I'm going to subtract it. Oh, that was the eraser. And I'm going to subtract it from here. And notice that a dot a for vectors is really just the size of a squared, right? So this part is the size of a squared, and I am subtracting half of it. So I'm getting half of the size of gradient of u squared minus rho u. Did I erase rho? I erased rho. Okay. And that is phi of u. That's going to be less than or equal to 1/2 gradient of phi minus rho phi. But what is this? This is by definition phi of v. Of course, I'm missing some integrals, but really it shouldn't matter. You should recognize that that one integral actually denotes 3 in this case. Okay, so this is all I have left to claim. This is my claim. Okay, let's prove it. Actually, this follows from the Schwarz inequality. What does the Schwarz inequality say? It says that for vectors a and b, a dot b is less than or equal to the size of a times the size of b, right? This is by Schwarz. Sometimes Cauchy-Schwarz. Anyway, now this right side is again less than or equal to 1/2 of a squared plus b squared. Why? Why? What happens when we take a minus b and square it? Well, whatever this is going to be greater than or equal to 0, right? And if we actually multiply this out, this is going to have a minus 2ab term, which we can move over to the right side and then divide everything by 2. That's why there's a 1/2 right here. Okay, so letting a be the gradient of phi and b be the gradient of u, by this inequality that we just proved, we have our desired inequality that phi of u is always less than or equal to phi of v for all v in our set. And therefore, a is the argmin of our Dirichlet functional.